to do something. Time to do something. What I got for today is Earth fault protection for isolated neutral network. Who they are and why they are interesting. The idea is, if we assume a network with isolated neutral, for example, free wire, our load can be, say it's A, it's B, and it's C. Delta connected with delta star transformer or isolated star, grounded star transformer. If load is symmetric, not very asymmetric, everything will work fine. Why I'm drawing here? Take a look. If we have an earth fault, for example, here in C phase, what will be current? In theory, because there is no ground port, current will be zero. Reality a bit more complex. In reality, network has a phase line to ground capacity. So, there will be a current to the ground, from the ground, from the ground. Current to this held wire to ground capacity. But this current will be small. Current will be limited by network capacity. Yes, we will see a shift in voltage. If, let's say, A, B, C, this was voltage star against ground before fault, I have this value. So the 0 point will shift. This will be B voltage and this will be C voltage. It's again ground. But we have delta here. Line voltage do not change. The neutral point, 0 point, it's a if we plug voltmeter here, it will show us shift. But line voltage do not change, so load continues operation without any disturbance. Such kind of network gives us one positive thing. We can continue operation even in case of ground fault. General, at first moment, at first look, there is a limit current in the here. Current at the fault place. Old rules allowed to operate 8 hours without doing anything if current is less than 15 amps. Higher current can damage something, wire or something like this. So such kind of networks offer us good statistics. We have a fault, And Earth's fault is most probable. And we can continue operation. So why Earth's fault protection is needed? You can ask a question. Is it in general, in all time, it wasn't needed. Only a signal from free pole to zero, what we have a fault. And we had 8 hours or more to find this fault and do something. Nowadays, not so easy. And why not so easy? See, current of 10 or 15 amps isn't danger, do not pose a danger to network itself at first. Let's say in our approach, actually there are some moments we have voltage rise in Earth's fault. Here, line to ground voltage in its steady or enforced component will be 1.7 square root of 3 times higher, and instantly in the fault moment during the transient it will be 2.6 times higher. It can cause insulation damage. But really, network can operate. Another problem, what it is possible, what this fault is a human. Earth's fault current is dangerous to humans. So in populated areas, now, risk management strategy asks us to clear this fault, to disconnect line. Because it's dangerous to live being. So protection is needed in inhabited areas. Also, line disconnection and reclosing, fosters fault clearance. If fault was caused by, let's say, very often 3 branches or another thing, quite often it's reason. People throw thin wires and other conductive objects. Also, what often happens in areas where large birds prefer to nest on the poles, the effects cause this kind of faults, creating a conductive breach of insulation. If you clear the fault and then switch it back, it's highly possible that arc discharge will be ionized and it will be possible to continue operation. So now we have a request for protection. Protection able to clear Earth's fault. I will redraw my schematics. Let's say we have something like this. Transformer, I don't know, it may be 10 or 20 or name it. 10, 11, 15, 12, so-called network, but network with isolated neutral. Isolated neutral network. Kind of distribution network. 1, 1, 2, and Earth's fault. Let's take into consideration something like this. 2 lines and Earth's fault. Here are my A, B, C box. line 1, line 2. Capacitance, capacitance, capacitance. A phase of second one, B phase second one, C phase second one, first one, B phase first one, and A first one. Here is my set of capacitance. This is transformer connection, not important. What's important? Let's say I have an, here is my earth fault at a phase E, A. What happens? Let's try to trace currents. It will go to transformer, and should I draw a transformer? We will see it here. Here is current number 1. It's let EB1. I can draw comes back. It will be 1. Also, I will see this through current through this capacitor. It goes here, 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 and it will be IB2, and current through this capacitor. Hop, 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 it will go, I will see it here as IC2. Can I need to take some current, some signal for my protection? Can I use phase current? No. All this in some, let's say 15 amps. Load current, 1000, 2000, so I will see nothing. I need to take a zero sequence. The only choice for me is to analyze zero sequence current. And for zero sequence current, I can draw it. Here is my, let's say, contour or loop. I need some, here in my blue ring, I need A phase plus B phase plus C phase. This will give me triple zero sequence current, the only signal I can rely on in this situation. And what this current contains? Take a look. On orange, on orange. On blue, on blue. My own current appears to go backward, forward. Backward, forward. Appears extremely strange. I will add. I can rely on this current and this one. Maybe I to make it more visible, I will mark it in yellow. Where is my P2? This one. You see what happens? Very strange thing. What inside the loop, where I take zero sequence current, in reality, appears what on this line. Current, how to say, defines what I will see. This is quite strange. I drawn this just to show what analyzes in phase coordinates is actually a waste of time. If I would like to get good results, I need to switch my analyze space. The best idea I know is to analyze in terms of zero sequence. Again, my network 1-1 with ground fault and 1-2. Say it's a distance of alpha. At a first glance, my zero sequence schematics will look like this. By half can look like this. Alpha 1-1. Point of M here. Alpha CL1 by half. 1 minus alpha C0 L1. This one. 1 minus alpha C0 L1 by half. And another capacitor it's this is not to ground but to N0. This one again 1 minus alpha C0 L1 by half. A point, it's a bus, and on the other side, C0 L2 by half, continuous with Z0. This also is zero sequence resistance, and this one is 1 minus alpha Z0 L1. And again, C0 L2 by half connects here. And here inflows a direct sequence, outflows a direct sequence. Here is with precise model of this network. Only zero sequence. But I draw it once just to represent. There is one moment. Moment is connection. What these capacitance are relatively small, and resistance they introduce, its absolute value, is much higher than the line resistance. Meaning what I can use a simplified schematic. It's absolute adequate C0 L2 point A where the buses are. This amperemeter shows zero sequence current of our relay. Zero sequence voltage of our relay, it's a point of bus. Next one, this capacitance is alpha, zero sequence capacitance of L1, M point connection point, one minus alpha, zero sequence capacitance of L1. Again, simplification. I can actually ignore resistance of direct and negative sequence because they are much smaller when resistance introduced by this zero sequence capacitance. The EMF of direct sequence. Here is my current. And what determines it? Watch. The current through protection, the current available to my relay is determined by capacitance of non-damaged part of network. Here you can see it absolutely clear. The current I observe is determined by undamaged part of the network. Yes. There is actually no depends from alpha. Really. I'm in a maybe shake situation. I cannot use current magnitude to create a selective protection scheme. The only thing I can rely on is a direction. I need some kind of current threshold because there is a zero sequence current in normal regime due to network asymmetry. Capacitance of phase toward ground, let's see, A, B, C, are not uniform. Meaning what I will see some zero sequence in normal mode. So I need some current threshold to prevent false operation. but for selectivity, current is useless. Current through fault is determined by capacitance of healthy part of network. It's important to understand when we speak on such electrode protections. How can my schematics look like? Hello. Lately? Here I speak on electrode protection for isolated neutral networks. And one of the very important moments of current through protection relay is determined not by fault place, but by capacitance of healthy part of network. I don't know, in your country, maybe back to ask, in your region, distribution networks are grounded neutral or isolated. You have one barrel transformer for each customer, or three-phase transformer for a group of customers. Three-phase, that means what highly possible you have, highly likely you will have an isolated neutral. American style, where each customer has its own barrel kind of transformer, they operate with grounded neutral. If you have European style, isolated is more probable. Okay, so what I spoke, it's useless to analyze such networks in phase coordinates, and we should switch to analyze in zero sequence terms. Here I have two lines, one fault at a distance alpha per u, and simplified zero sequence schematic shows us what current through relay, if relay sits here, will be determined by healthy part of network. So what can I do? If I can't use current magnitude as a selectivity value, I will need to create schematics like this. For example, this is my transformer. Line. And, not important, healthy part of the network. I will need here on each station plan a relay what will combine what? E0 greater to prevent false operation from network asymmetry, plus zero sequence angle should be in some region. This zero greater should be selected to ensure it should be less when capacitive current from non-damaged part of network, but greater when current of non-symmetry. So this is zero. It can be uniform for in and only thing. It should be greater or equal 1.1 non-balanced zero maximum. It's a small value, hardly to predict. Usually just measure it. it's hard to calculate, but it will be somewhere, I don't know, 5 amps of primary is a high value. With angle we will speak, but what we will do, we will set trip time. We will achieve selectivity with time scale. 1 delta t, 2 delta, 3 delta t, and so on. Because we can be lazy. We are not required to operate instantly. This type of protection, good practice for this type of protection, keep trip time at last above 100 milliseconds or more. Because what can be? First, trip of overvoltage limiters. Second thing, in a rainy time, there can be a flashback of insulator, but if you have a good insulator, moisture will dry and you can keep operating. So, trip time less than 100 milliseconds, usually it's somewhere second or more. Even for faster stage. This type of protection is lazy. 1. Now, what about direction? What do we need? What do we need? We need to prevent backward operation. We need to prevent operation in case fault is here. We will see current. Again, current, zero sequence current is determined by healthy part of network. So there will be a current here. We need this protection to be polarized. What kind of, what we will see? We will see a capacitance. And here, read carefully your protections manual. Exactly. Because they are, in reality, they are protection devices using zero sequence voltage and negative or inverted zero sequence voltage. Characteristic can be like this, or its mirror. If this is zero sequence voltage, or it may operate on minus zero sequence voltage. So depending on your relay design, check which characteristic is correct. Capacitance or minus capacitance. This distance is E0 minimum. It's a minimal trip current should be greater than E0 non-balance. All type of relays had an angle 180 degrees between vanes. Modern practice is to take it smaller, from 130 to 150 degrees, just for safety. During the arc transient, if, for example, we have a very only single line and arc transient, current will be real. It's assumed a possible false trip. I'm not 100% sure. can be discussed, but common practice based on statistic is like this. So operate assumes what fault loop resistance is pure capacity. There is couple more moments about, with this protection. Where are you? Transformer. Here he is. Zero sequence transformer or cable transformer. Cable. For example, cable should go like this. Earthing, screen earthing wire should go back through transformer to prevent self-operation from ground currents. Here it is. This is your source of zero sequence current. Do not try to use phase transformer. Non-balanced current will ruin everything. You will have no sensitivity. But where is the tricky moment? Earth fault currents are small. Imagine, one more. You have network 600, 1000, 2000 amps of normal current. Earth fault, 15 amps, okay, 20 amps. Nothing in comparison. You need to have quite sensitive relay. Yeah? And there is one tiny moment. L1, A, B, C. Here is loop of your current transformer. Sits on a cable going and 1, 2, 3, A, L2, B, L2, C, L2. Here is the loop. It's, let's say, 1, 2, relay 1 to relay 2. Earth fault. What kind of current will be transformed to relay? Zero sequence current of this line, yeah? Some amps. What can happen? I will draw it again. Before the fault, a ground voltages relative to ground looked like this. Here was our zero or neutral point. At the moment A phase connects to ground, what happens? Zero point goes here. And this will be C voltage, and this will be our B voltage after the fault. Neutral point goes up. Voltage in forced component, or steady components, rise 1.7. In the moment of transient, it will rise to 2.6 average. Possible what insulation of this part. Nothing is forever. Dies, and we got second Earth fault. Double ground fault. In reality, it's what it now? Line to line AB fault. If Earth fault was, I don't know, 15 amps, this one will be 2,000, 5,000, 7,000 amps. You see real current of the true line-to-line fault. Current here will be not milliamps, it will be dozens of amps. Problem of double earth. Double earth fault is actually a line-to-line fault with a high current. So your relay should withstand this current. One of the problems of such earth fault protection, they are required to have very high overcurrent capability or resistance. In early version it was done with saturated transformer. In modern versions, special limiters in the input stage. Otherwise your relay will burn. Not every overcurrent relay is suitable for such kind of protection. One moment. Okay. Problem of double faults. You need a very high your inputs should be able to withstand very high current rating. Sensitive, but with very high possible current. It's problem number one. Problem of double fault. Problem number two is so-called intermittent arc. It's often observed on old paper oil cables. You have copper conductor, layers of impregnated paper, and let's say outer shield. Here is the damage. Lead shield due to corrosion or lens shift cause a break, cracks in the shield. So what happens? Water gets in, forming a conductive bridge. Earth fault. What happens during Earth fault? All the network capacitance discharges through this place. High current causes what? Heat effect. And all this mixture of water and oil been thrown out. Sometimes what happens, at first moment it breaks through. Heat effect of current causes this cable wax to melt, and seal the place of fault. But if it shells out, it throws out conductive elements, water and what else, and insulation returns for some time. Often, current of such fault looks like this. It shows there is often no constant current, but series of pulses. If you use simple, ordinary directed relay, it's highly possible that it will return falsely return, and protection will never operate. So to prevent false operation due to intermittent arc, special measure should be taken, and its measure is a delayed return. So schematic, first one schematic of such protection. Zero sequence current, current limiter. Special circuit prevents damage in case of double line fault. Zero sequence voltage. One or more stage, zero sequence current generator. Can have multiple stages. For example, can have two stages, but actually one is enough, because current again, healthy part of network determines this current. Multiple stages are absolutely redundant. The only, in third time, role of this element is to prevent false operation from network non-symmetry. Characteristic, angular characteristic. Angle between zero sequence current and zero sequence voltage. Next, delay timer. At last, 1/2 of delta T. This timer prevents false return during the intermittent lock. Delayed return. Delta T timer. Here's first schematics of such protection. Requires current limited and delayed return timer to prevent false return due to intermittent current. This was easy. When people started to think about reliability of network, reliability of supply, what can be done? I need to continue operation during a fault. If fault current is small, I can continue. If fault current is reach dangerous levels, something should be done. And technique called compensated network was introduced. I will kill someone. Do not disassemble any network under voltage. What I wanted to say, I wanted to draw. I wanted to draw one thing. Say transformer 1 1 1 2 Earthfold. Distances of our zero sequence network. Zero sequence capacitance of second line. A bus. Alpha zero sequence capacitance of the first one. 1 minus alpha zero sequence capacitance of the first one. And this one here will follow direct sequence. This is fault place. See the schematics. What can be done? Current here flows fault current. What kind of resistance do we see here? Capacitance. pure capacitance, yeah? If, let's say, we add a coil here. Capacitance, 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 coil, net voltage, sum of capacitance current, yeah, coil current. If I select coil inductance in way that coil current will be equal to sum of capacitant current, what will be current in fault place? 0. This thing is called resonant network or resonant neutral. Better use this term, resonant neutral. Peterson invented this. So this coil is often called a Peterson coil. With the help of Peterson coil, I can reduce fault current to 0. This will be 3 omega L Peterson or compensation coil. Compensated neutral. I can compensate capacitive earth fault current with inductive current. So, some resulting current will be 0. How it can be done? We have isolated network. Okay, say delta transformer you need to create such network, you need a special trick. You need artificial neutral. This network by definition don't have neutral. Here how it's done. You take a small 20, 10, 12, max 50 quad transformer with star delta connection. It's important because 0 sequence current will circulate in this delta. And at the neutral point attach your adjustable coil. Sometimes they came with transformer. Here in our local practice we prefer to buy them separately. Coil with adjustable inductance, it's motor driven. And special net transformer to create a neutral. This is how compensated neutral is created, or Peterson neutral. Usually, to prevent overvoltage, EL is approximately 105. Some are special automatic adjusters are available on the market. But there is one problem. In such kind of network, it is virtually impossible to detect fault direction. If you have isolated neutral network, capacitive current will give you direction. In case of compensated neutral, directed fault protection in its simple form will not operate. You will have no current. Or you can react to coil current and give wrong direction. So for such kind of network, simple kind of this characteristic will not work. What can be done? There is no silver bullet. One of the approach use not the 50 Hz component, but 150, third harmonic. There will be no network compensated or resonant. At 50 Hz is not compensated at 150. Coil resistance 3 times higher, capacitance resistor 3 times lower. So one of the ideas is use 3 ohms. In our case, 150 Hz. Such relays are manufactured, they are available on market, but there is no guarantees that there will be enough level of third harmonics. There were some ideas where coil were equipped with non-linear resistance. Not always such relays are 100% reliable. Also, as more as theory. What can be done? Because whole network capacity discharges to the fault place, sensor, wide frequency sensor able to operate at all frequencies. Actually, you need to calculate amount of energy flowing through line during discharge. Because all discharge occurs through the fault place, the strongest signal will be on faulted line. But there is a problem because it's a very low, it's exponential. Signal is very low. And one more tricky moment. In theory, at the first time, current through coil is 0 because of coil inertia, but it's in theory. In reality, it's dependent on coil design. For coil with air gap, it's okay. For coil with magnetic shunt, something like this, it's not okay. When the darkest beginning, see, if you take coil with steel core, transient has an interesting behavior. At the first if you take this coil in steady or stable regime, coil self-inductance EMF, or to say it's in equilibrium with outer voltage. At the first moment of transient, there is no magnetic field in the steel, and steel has its own has inertia. At the first moment, there will be no magnetic field and absolutely different level of inductance. So it can be tricky, but sometimes it works. Anyway, you should understand what? If we deal with compensated network, protection, simple directed protection is unreliable. On market available designs for third harmonic also using can be exist design 5 omega plus 7 omega, something like this. Design on higher frequency. again, not 100% reliable. Much depends on higher harmonics level in your network. In industrial areas, work. In some rural, no. Okay, what can be done? One of the tricks is to create a current component directed towards fault place. This can be done. One of the techniques is to equip coil with a secondary winding. And have active resistance here. Usually something about 500 volts and active resistance. What it will give us? If here is our voltage, capacitive current, compensating coil current, active component is always directed towards fault place. This component current through resistor, maybe I need to draw your zero sequence schematics will look like this. 1 minus alpha C0 L1 fault place, alpha C0 L1 bus point. Here is a zero sequence current of your relay. Here you will get C0 L2, non-damaged part of network. Inductance of neutral forming transformer. J omega. Peterson coil inductance and triple resistance. Here how your zero sequence schematics will look like, of course. This EMF is a phase EMF of direct sequence. I omitted direct negative sequence resistance because they change really nothing. So this current is what your relay will look for. Operational characteristic, you will need something like this. Active, oriented towards real arcs. This resistance is actually selected. For example, here in the Riga region, ER should be approximately 1000 amps. Good thing with in such network, they are reliable. Another good thing, this resistance limits, how to say it, its dampers network, its diminished resonance quality of the contour, equivalent fault contours, and its limits over voltages. It's good for network, how to say, network life. Model net so-called low voltage, low ohmic neutral, low ohm neutral, compensated network with resistance on the coil secondary winding. This gives very good operation of earth fault protection. One thing you better know. In reality, these resistance are not they are not intended for long time usage. They are not thermally sustainable. Usually they can be under load only for 5-10 seconds. They are for short time operation. Typical thing, bus, neutral forming transformer, Peterson coil, secondary link. This thing is activated by presence of zero sequence voltage, resistance. When resistance connects earth's fault, we have zero sequence voltage, resistance connect. When it should be disconnected? Your protection should clear fault. One of the mistakes people do, they start to testing, oh, let's find where it is by connecting, disconnecting lines. Or, oh yeah, we need to improve safety. This thing left operational, but protection is from disconnection mode switched to signal mode. Earth fault protection, or in old design, can be switched into signal mode when it only sends a signal we have an earth fault, but do not disconnect. Also, what mistake? High, they set a very high clearance time. Above light stand or thermal capacity of this resistor. And things are solved when this resistance gets damaged and no one bothers. If resistance is burned, what we will get? Answer, simple compensated neutral network, where earth fault protection do not operate. Be careful. If it's on your responsibility, make sure that this resistor is periodically checked. Otherwise, it can be damaged, protection will not work, someone gets killed, and you will be guilty. It all will fall on your head. Remember, 100% non-operation of earth fault protection caused damage or death. Protection engineer will be the one to blame. Will become, say, scapegoat. Make sure what this resistance is in a check plan. And operation of this switch is in the check plan. Okay, so where we are? Yeah. Low ohmic neutral is resistor a good thing in inhabited areas. Sometimes you would like to have a good protection, but customers, no cash flow from customers is low, and it is hardly to push management to buy this quite expensive oil. One of the tricks to reduce costs for network with small earthfall current, but you would like to have a good protection, is so-called high ohm neutral. Small transformer and only active resistance. We will see if this is voltage, this will be your capacitive current, and small ER to operate. Such resistors are manufactured air-cooled, like a skeleton barrel with wire around it, just to live on a pole above human hair, to protection of touch. High ohmic neutral. Neutral, the only active resistance. It's a good thing for small networks in inhabited areas. One more. One more thing. You have substation, line, nice network, low ohmic network, everything fine. Here, you have customer, our reality, who installed a photovoltaic system. Our nowadays reality, because it's profitable, we have a subsidy, local. People do install photovoltaics on their roofs. Let's say we have an earthfall here. We will see nice earthfall current, mostly from this point, yeah, and good operation condition for this protection. Really. And what about this one? Very weak current because capacitance here. Whoa. If this relay disconnects, will voltage disappear? No. We will still receive energy from this photovoltaics through back transformation, and fault will be energized. Its problem at this moment is solved. It's not solved. Actually, if we have a large customer park, they are required to disconnect the inverter. They are forbidden from island operation. They should discontinue supply if connection lost. it can be determined by frequency shift. But for small, no guarantee. At the present moment, what the only thing can be done here should be installed protection for isolated neutral mode. Sometimes what can be done, it's an idea of distributed compensation. Some Nordic countries do implement technique of distributed compensation. They install multiple Peterson coils around network. This bit improves economy, but key moment, if you have network separation, this still remains a low ohmic network. Classical network with one resistance, in case you have multiple sources, after trip of this switch becomes an isolated neutral network. So you will need protections here with characteristic for isolated neutral. Important moment. Relays intended for isolated neutrals and relays for ohmic neutral are not compatible. One or another. Be careful. With okay. Maybe some questions online? Is it clear? Yeah. Okay, that's mean what? Okay.